All right, so our first application derivatives thing that we've looked at so far was curve sketching. Now we're going to look at kinematics. That's the study of motion. Looks at velocity, acceleration, and distance. So a little bit of review. We know that the slope or gradient of a curve at a certain point, we can use the derivative to find that. So if we find the derivative at a particular point, that's the slope. And what slope is a rate of change of your rise over your run. So that's your derivative. Now when you're dealing with things like velocity, if someone says, well, how fast were you traveling? You were traveling on the highway, how fast were you going? You'd say, well, I was traveling 100 kilometers per hour. And when you have that kilometers per hour, you're talking about a rate of change. How many kilometers you go in 1 hour. A change in one thing over a change in another thing. So the rate of change of displacement and time, if you did kilometers per hour, that's your velocity. Now we know about average velocity. If it took you 2 hours to drive 100 kilometers, your average velocity would have been 50 kilometers per hour. But we've talked about this before as well. At certain points you were probably driving faster, and at certain points you were driving slower, especially when you started. Very few vehicles can go from 0 to 50 kilometers an hour in less than a second. That would be quite the experience if that did happen. So you have an average velocity over a certain amount of time, but when you take your derivative, you're finding out what that instantaneous velocity at a specific time is. So we use S for displacement, T for time, V for velocity. So that tangent is the instantaneous velocity, and you can find that by doing the derivative of any displacement equation. So if you have an equation that says this is how far you'll go after a certain amount of time, when you take the derivative of that, you find exactly the velocity of that same situation. And when you take the absolute value of your velocity, you get your speed. So here we've got some sort of object given by this displacement, t squared plus 3t. So we want to find the average velocity over the interval from 1 to 3. Now when time is equal to 1, and I plug that into my formula for displacement, I will be at 4 meters. And when time is equal to 3, my displacement will be at 9 plus 9, 18 meters. So does it make sense that I have gone 14 meters in 2 seconds? So as far as an average velocity that I've gone, I am traveling an average of 7 meters per second over that time. Does that make sense? If I've traveled 14 meters in 2 seconds, then my average speed over that time would be 7 meters per second. If I want to find the equation of the velocity, that's going to be my derivative. My velocity is going to equal my derivative with respect to time of my displacement function, which will be 2t plus 3. What does that mean? It means when time is equal to 1, if I plug that in, my velocity at that time was 5 meters per second. And when time is equal to 3, when I plug that in, my velocity is 9 meters per second. I'm traveling much faster at 3 seconds than I am at 1 second. So in part A, we could figure out what the average velocity was over that time period. In part B, we can see what the velocity formula is. And if you looked at your speedometer at 1 second and your car actually is in meters per second rather than kilometers per second, which would be very odd, but interesting. Kilometers per second. Kilometers per hour. This is what it would show. We are going to get a lot of questions that ask about initial things. What was its initial velocity? What was its initial displacement? Anytime we're talking about something's initial, we're looking at when time is equal to 0. So when time is equal to 0 in our velocity equation, which we had before, which is 2t plus 3, plug in 0 for the time, and we find out that the initial velocity of this was 3 meters per second. And if we want to find out when the time is equal to 4 seconds, plug that into your velocity formula, and you're at 11 meters per second at that time. So here's another example. In this example, we're given an equation. And there's some pretty cool things that happen in equations that you probably never noticed when you did quadratic functions. Okay? Now, in quadratic functions, that's something like this because it has a t squared. What happens is you throw something up in the air, gravity brings it back down, and it hits the ground. The path that that object travels, if you would graph a height versus time graph, always makes a parabola. But now we can observe some interesting things in that parabola by doing this question. So we've got its initial displacement, and in this case, its initial displacement is given by this formula, 122.5 minus 4.9 t squared. If we want to find the velocity after 2 seconds, well, our velocity is our derivative of our displacement function. And if we do the derivative of this displacement function, what do we get? Negative 9.8 t. After 2 seconds, if we plug 2 into that, negative 19.6 meters per second. Do any of those numbers jump out at you? Yes? Negative 9.8 is the force of gravity, right? Negative 9.8 meters per second squared is how much gravity changes. And whenever you did these application questions in grade 11 pre-calculus, and you had these formulas, your equations would have always had, if they were trying to be realistic, if they weren't trying to make up a question that was on the moon or on a different planet, they would have always had negative 4.9. Sometimes they would have written negative 5 just because they didn't want to make the question too difficult for you. They would have put something in it to show gravity. Because when you take the derivative of this, you get a velocity of negative 9.8 t. If you take the derivative again, you will just get negative 9.8. And in fact, we're going to find that out later. I'm spoiling the notes later on, that the derivative of velocity is acceleration. And so if you always have a displacement function representing something in real life, you will have that negative 4.9 t squared in there. And when you take two derivatives, you will always get an acceleration of negative 9.8 meters per second, if you're dealing with something that has to do with gravity. So that's kind of really neat. The other neat thing that will show up in these questions, it doesn't happen in this one because we don't have another value of t, but if I had written this situation out, let's say I have everything the same in this equation except I have a plus 10t and then a minus 4.9 t squared. Your first derivative, your velocity, would still be negative 9.8 t, but then you'd have plus 10. Whatever number is here When I plug in 0 into my velocity equation, this goes away. That number shows up there, and that's always your initial velocity. So in the equation I wrote off to the side there, that would be the same situation, but instead of just dropping the stone off a cliff, where dropping the stone off a cliff would have an initial velocity of 0 because you're not doing anything to it, this equation that I put here would be throwing that stone upwards with an initial velocity of 10 meters per second. And then gravity would act on it and start pulling it back down. So a couple of things here. We have directions involved. The negative is what we show by having something going down towards the ground. A positive value would be a force upward. So we have positives and negatives here to help us understand that. So what's going to happen is you're going to take derivatives, you're going to get velocity equations, you're going to take another derivative, you're going to get acceleration equations, and when we solve questions, we're going to have to ask ourselves, which of our equations do we need to use, and how can we set up that equation to help us solve this? So for part B, and I'll erase this because we don't need this, this isn't part of our equation. For part B, we want to find the time when the stone hits the ground. Are we going to want to use our initial height equation, or our velocity equation, or our acceleration equation when we're trying to figure out when the height hits the ground? Or sorry, when the stone hits the ground. We're going to use the initial equation, right? And what do we know about the initial equation? We want to find t, so we don't know what t is yet. But we know that the height, when it hits the ground, will be 0. So we can set it up. Can you guys see that the height of this is 122 point, when you're dropping the stone initially, that this cliff is 122.5 meters high? Because if we put 0 in for time, that would be the initial height. Now solving for this, divide 122.5 by 4.9. And it is look at that, isn't that a nice number? Square root both sides. When you square root both sides, technically you should write plus or minus, but you can't in a real life situation. Maybe I'll show the plus or minus, and then the only realistic answer is 5 seconds. This would be the actual formula of this situation. If you were on a cliff 122.5 meters above the ground and you dropped a stone, it will hit the ground in 5 seconds. Bearing that you're not having, you have a nice stone that isn't like super flat, that air resistance can make it have some effect on it, because those things do happen in real life, and it's not a windy day where the wind is going straight up, those kind of odd things that happen every day, once in a while. Those things would affect your equation. But in an ideal situation, we can now just make an equation for that. Dropping a stone off a cliff, it will hit in 5 seconds. And all we needed to know was gravity, and that shows up by the negative 4.9 t squared, and that we're 122.5 meters above the ground to start with. And then you could even figure out things if you knew how to launch that rock up with an initial velocity of 10 meters per second, because you've been practicing. Or you've gone to the batting cages and you know how hard you can throw. So you throw it upwards as hard as you can and know its initial velocity. Then you could predict how long it's going to take for it to hit the ground. Yeah, probably. How fast is that stone going when it hits the ground? So you tell your buddy to lie on the ground at the bottom of the cliff. You got your stone, and you say, catch, and you drop it. And he's waiting at the bottom with his hands out to grab it. How fast is it going when it hits his arms? Okay? Don't try this at home. So we've got our velocity equation, which was negative 9.8 times t, and it took 5 seconds to go down there. So if we multiply 9.8 times 5, it's traveling negative 49 meters per second, right? You could change this to kilometers per hour to figure out how fast that would be, like a car hitting you. Because I don't know how fast that would be. I mean, what's the world record for running the 100-meter dash? It's just a little bit less than 10 meters a second, right? Because it takes them about 10 seconds. So this is going 5 times as fast. So if you think maybe you want to experience this, stand at the finish line when Usain Bolt 100 meter, let him run right into you, and then just imagine this would be 5 times faster. So there you got a little bit of an image, and it's just a single stone, as it's so. So we already talked about this, that if you take the derivative of velocity, then you get your acceleration. And we saw that in that last equation when we just get negative 9.8 meters per second. If you were doing questions, American questions in grade 11 pre-calculus, they'll have like 15 or 16, because that's how feet per second instead of meters per second. So sometimes you'll see that in equations, and you go, oh, this equation isn't right, but it might be in different units. I can go back for a second, yeah. So we can write acceleration as the first derivative of velocity. We can also write it as the second derivative of displacement. So I'd like you to try this one on your own. I'll put up the answers in a second. So our velocity is going to equal the derivative. So once you've taken the derivative and then plugging it in when time is 1, you'll get 24 meters per second, which you can write as either meters per second like this, or you could write it as meters per second like that. Either way is fine. So when a particle is at rest, it's not moving. The only way something cannot be moving is if its velocity is equal to 0. So if we set our velocity equal to 0, which is our derivative, and if we solve that by factoring, take out a common factor of 3 to make your factoring easier, then you're going to find out at 3 seconds and at 5 seconds, this object is at rest. Now, anytime an object switches directions, it has to stop, even if it's for a split second. So when you throw something up in the air, there's going to be a moment where it switches from going up to coming back down, and at that moment, it's temporarily, if for only an instant, at rest, because it's switching directions. Same thing if I'm walking one direction, turn around and walk the other direction, there was a split second in that I wasn't moving. My instantaneous velocity at those moments would be 0. Now in this one, it makes sense that there are two places that it's at rest, because if we think about our original graph is a cubic graph. It would look like this. It would have a local maximum and a local minimum. If we wanted to use our curve sketching to find that local max and that local minimum, we would take the derivative, we would set it equal to 0, and we would solve. Well, we did that thing right here because our derivative is the velocity, and by setting the velocity equal to 0 and solving it, we find out that at 3 seconds and at 5 seconds, this object is at rest. Now, knowing that, we can do what's called a motion diagram. Motion diagram looks like this. It basically says, well, let's find out where it is when it's at rest, when it changes direction. At 3 seconds, it's at 61. At 5 seconds, it's back at 57, and then it goes on from there. We know at time 0, if we plug in 0 into our displacement function, we would get 7. So maybe this is an example of an interesting 100-meter dash. Someone is cheating. They're starting 7 meters ahead of everybody else. The gun goes, in 3 seconds, they're already at 61 meters. They are traveling really, really fast. They're on a world record-breaking pace, and then they drop their cell phone, or realize they've dropped their cell phone. They dropped their cell phone at 57 meters. It took them about 4 meters to slow down, turn around, pick it up again, and then start running towards the final. Maybe they still won the race. We'd have to figure out how long it took them to get to 100 meters, if they were under the 10 seconds or not. Of course, they'd probably be disqualified because it'd be pretty obvious in the 100-meter dash if you started at 7 meters ahead of everybody else. I can just imagine, like, hope no one notices. So what this is showing is sort of the same thing that our graph shows, but your graph with distance over time doesn't represent something going horizontally. So if you wanted to measure something as it's traveling horizontally, you could still show that same idea of a cubic function, but this is showing that, okay, at 3 seconds it changed directions, and then at 5 seconds it stopped and changed directions again. And this is called a motion diagram. In this case, of a very unique 100-meter dash. That's why most racers never carry their cell phone. Watch. Go back on YouTube. Watch as many 100-meter dashes. You will not see a single cell phone on them for this very reason. Okay. So for our acceleration is just going to be the derivative of our velocity function. So we take our velocity function, find the derivative of that. And then plug in 1, and you find out that at 1 second, negative 18 meters per second. Yes? Yes. So that, because the sign here shows a decrease, where there was positive 18 meters per second, that person would be increasing in their speed. So the negative 18 meters per second means their speed, their velocity is decreasing, they're decelerating. And then, if we find out when that acceleration is 0, it's at 4 seconds. So if they were slowing down, eventually they'll speed up again, but then their acceleration would have to go to 0 in between there. and then everything after 4 seconds has a positive acceleration. So then you would see that as going faster and faster and faster. What does an acceleration of 0 represent in our graphs from before? That's going to be right here. That's an inflection point. So again, a very interesting race because this racer has an initial velocity. As soon as that gun goes, they're traveling at 45 meters per second. They've cheated, and boom, poof, they're off. But they use so much energy just getting to that instantaneous velocity of 45 meters per second that they're like slowing down. And they're slowing down until they drop their cell phone, and then they really slow down. Then they realize, as they're running the wrong direction, that the people behind them are catching up. So then they start accelerating again, grab that phone, head to the finish line, and win the race. Now I'm really curious to find out. You could type this into your graphing calculator, put 100 into y2, and that'll draw a horizontal line at 100. Find out where they intersect, because that'll tell us the time that it took them to get to 100 meters. And you could find out if this would be a world record-breaking race or not. All right. So here's another one I'll get you to try on your own. I'll put up the answers in a second. I have to apologize for my vivid imagination. Makes the questions a little bit more fun if you can. Oh, 7.73 world record. Why is S for displacement instead of D for distance like you would think? I'm not sure. Just a lot of textbooks use S for, maybe the first person that heard it just heard displacement. I'm not sure if that was the reason. Maybe because if you use D, then you'd have DD, DT. It just would be, instead of DS, DT, I'm not sure if that makes it easier if the letters change. Who knows? Oh, I've been recording this whole time. I meant to pause it in between. Oh, well. That'll be a lot of nothing in there between. Welcome back. So you can fast forward that. There we go. All right. So get your velocity by taking the derivative, set it equal to 0. Did you find t equals 3 and t equals 1? Yay. Should probably add some units here. 3 seconds, 1 second. I can go back, yep. I know, all of a sudden it'll be. And I probably said all those things about vivid imagination and, oh well. Don't expect this video to get record-breaking views. Maybe that part. I didn't say anything mean about anybody during that time. I usually am pretty good about pausing that and then then it's all good, right? Okay. Good? Fine. So at 3 seconds, the displacement is 5, and this was meters, right? And 9 meters. So that can help us with our motion diagram. So at t equals 0, we start at 5 meters. We start traveling in one direction, and then we change directions at 9 meters, go back, all the way back to 5 meters, and then forward again after that. So again, the motion diagram just helps give you a sense of what's happening to this object. If this object was traveling all in one direction, forward and backwards. And finally, we can find the acceleration at these times. So we're going to take the last 20 minutes to work on those practice questions.